everyone's
Nope.
Okay, great. So today we are very happy to have Seth. I've known Seth a very long time, since passing. We're roommates of sorts. So, well, we were.
We were just roommates. Of sorts.
Of sorts covers all of them.
Yeah, sure.
Yeah, okay.
We don't need to know the more details.
Of sorts. So, yeah, Seth did their PhD with Nathaniel at Santa Barbara, and then moved on to Chicago, and is now at Notre Dame, and is going to be telling us all sorts of interesting things about generalized global symmetries and non-perturbative quantum flavodynamics. So
Thanks so much, Rob, for the introduction. And yes, I was very pleasantly surprised to receive an invitation from Evgeny to come visit again. It's a fantastic place for particle physics, and for me to visit. I've already had some great progress on projects I'm doing with Rob and Donghoon just while I've been here. So it's fantastic. And I'm excited to tell you about this work I've been doing to try to understand some concepts and some technology from formal field theorists and really make use of it in particle physics. I should say what I'll mainly be telling you about is a couple of papers that are with my fantastic collaborators, Sungwoo Hong, who probably many of you know, and Clay Cordova and Kentaro Mori are a more formal field theorists. It's really been a fantastic collaboration. There's lots more and more things coming, of course, as well. Let me give you just a brief outline. Of course, this is going to be a particle physics talk, but I'd like to spend some time in the beginning really giving you some motivation for this idea of generalized symmetries and how to think about it, and what interesting things in general you should expect to learn from them before actually getting on to what we have concretely found by making use of them, which I am also, of course, very excited about. Okay, so let me start with some very broad motivation that perhaps here you guys need less than in other places. But, most of the time these days as particle physicists now, we are doing perturbative quantum field theory, right? You expand around some vacuum state, you calculate an S matrix for Fock-based states. Fantastic, that's all great, of course, but there's tons of interesting physics there. But it's also the case that quantum field theory is richer than perturbation theory. And sometimes it can really be the case that there are field configurations that are very far away from the origin in some sense, and that really matter. Just some very brief examples, probably something everyone is familiar with. If I just take a theory of a real scalar that spontaneously breaks a Z2 symmetry, then there are these two distinct vacua. You can classify this with a topological sort of quantum number. The zeroth homotopy group here is Z2. And what that leads to is some interesting physics that can happen, say, in the early universe of some domain walls, a certain type of topological defect separating these two distinct vacua from this, because we have this disconnected vacuum manifold. That's probably very familiar, maybe something to bend your mind just slightly more, an only slightly more complex case. If I just have a complex scalar that spontaneously breaks a U1 symmetry, now if I look at the vacuum manifold, it's not disconnected, but it has sort of a higher notion of disconnectedness. A first homotopy group being non-trivial, that is, you can map circles winding around the minimum of the potential any integer number of times, and this leads to another type of topological defect known as a cosmic string, around which the phase of the scalar might go around internally in its potential. And there's also lots of fascinating physics and cosmology in cosmic strings as well. But really the point here is that you can't avoid thinking about extended objects. They appear in very simple and also very realistic theories beyond the standard model from some sort of interesting topological effects in our, often in our gauge theories when you're thinking about, say, some interesting grand unification. So these fundamental extended objects are often in our theories. Now, I surely don't have to motivate to everyone that symmetries are very important, always in physics, and especially to us as fundamental physicists, as particle physicists. And usually when you think about the symmetries of your theory, you do so by looking at the Lagrangian data of your theory and thinking about transformations of local operators. And of course, that's great, but as I've just motivated for you, many times, very often, our theories have these extended operators that's associated to some topological data in our theory. And so it's a natural question as to whether there exists a notion of global symmetries for these extended operators as well. And the answer we know now is yes. And there's this fantastic paper from now a decade ago that really set out this program in full of generalized, well, in generalized global symmetries. And so the basic notion here related to symmetries that act on higher dimensional objects is what's known as a higher form symmetry. The familiar symmetries that we all know and love in this framework are known as zero form symmetries. They act on zero-dimensional local operators. And as you know, such a global symmetry has a conserved current with one index. But indeed, whenever there are higher dimensional operators around, they can enjoy a notion of higher form symmetry. For whatever sort of operator, actually the most important one for us today will be the one form symmetries that line operators can enjoy, like Wilson lines or 't Hooft lines, which, just to remind you, you can think of as the world line of some heavy charged, electrically or magnetically charged particle. When you take the mass to infinity, then these line operators sort of encode the response of the system to that particle on that world line. And good, these line operators can enjoy a notion of one form symmetry, and this also has a conserved current, but now it is a conserved current with two indices here. And I'll get on to a concrete example in a moment that will make this very familiar. But let me just pause to say immediately why you should think maybe this is quite interesting to learn as a particle physicist. Because let's just think briefly, and I'll come back to this as well, briefly about breaking these symmetries. If I want to break a zero form global symmetry, since the charged operators are local operators, I can do so by adding a charged operator to my Lagrangian, right? If I add a Majorana mass term for neutrinos to my Lagrangian, I explicitly break zero form global lepton number symmetry. But what about these higher form symmetries? The charged operators here are extended operators. These aren't the sorts of things that go in your Lagrangian. And indeed, there's no deformation of the Lagrangian that you can do that will explicitly break these global symmetries. Rather, these sorts of symmetries break only when you go to further UV scales, to higher energies, and you see the appearance of new dynamical degrees of freedom. And this is a big sort of qualitative difference. And indeed, the mileage that I'm going to get out of this eventually later in the talk is going to be playing with what we're able to understand by how higher form symmetries break in some special circumstances where the higher form symmetries can get intertwined in a sense with the zero form symmetries and give us more information about zero form symmetry breaking than normally we think is in our theories. Okay, but let me expand on these basic notions of generalized symmetries in a more familiar context. We can think about a very simple theory of particle physics, just pure electromagnetism, which actually, in fact, has some rich spectrum of generalized global symmetries. Let me remind you of Gauss's law, as we all learned as children. In undergrad, you would have seen this spatial picture of Gauss's law. And Gauss's law tells you that this Gaussian surface, a two-dimensional spatial surface that you can draw, is topological. It doesn't matter what size or shape you make this surface. The integral of the electric field over that surface is invariant, and so it computes some sort of invariant charge. Now, actually, you might have always been a little bit confused about what sort of charge this was. When you went and learned quantum field theory later on, the sort of global symmetry charge that you learned about is a Noether charge. But nurture instructs you to integrate over all of space at a given time. You're integrating over a three-dimensional manifold. And that's manifestly not what Gauss is instructing you to do. So you might be curious exactly what sort of symmetry charge this is. And we can get some insight from thinking a bit about higher form symmetries. In fact, in pure electromagnetism, as you know from the photon equation of motion, the photon field strength itself is just such an antisymmetric two tensor that obeys a conservation equation, right? And that means, indeed, there is a one-form symmetry in pure electromagnetism. One-form symmetry should act on line operators, on one-dimensional operators. And indeed, thinking more in a covariant sort of picture, really anytime you were using Gauss's law as an undergrad, what you really had in mind is that there was some heavy charge in your space-time it was some Wilson line in your space-time. The point here is just where it crosses that time slice. And your Gaussian surface can always be, this integral you do can always be written as the integral of this one-form symmetry current, or two-form tensor, which is the current for the one-form global symmetry, over some two-dimensional surface, and you get a non-zero answer when this links in some four-dimensional sense your Wilson line. And now we have this on just the same sort of footing as is familiar from Noether's theorem. Noether instructs us to integrate a current over a three-dimensional surface, a normal one-index current. Here, we are integrating a two-index current over a two-dimensional surface. And indeed, Gauss's law, in fact, does compute a Noether charge, but it's a Noether charge for a one-form symmetry. The charged object is not a local field, it is a Wilson line. That was always what you had in mind, really, when you were using Gauss's law in electromagnetism. Okay, and now let me go back to breaking these symmetries. In fact, I was careful on the previous slide to say pure electromagnetism, because this electric one-form symmetry is an emergent symmetry of the real world, right? In the low energy distance, low energy limit, where you're far below the electron mass. And the easy way to see this is when you're in pure electromagnetism, the only gauge invariant line operators you can write down are some closed loops or some infinite world lines. But once you go to higher energies and you see the dynamical electron field, then you can write down some gauge invariant Wilson line, which ends on, say, a positron and an electron field. And then it simply must be the case that Gauss's law breaks at energies above the electron mass, because now there's no chance that this Gaussian surface could compute something that's truly topological. I should have emphasized, I meant to say I should emphasize on the previous slide, the spatial topological invariance of the Gaussian surface in this fully covariant picture is upgraded to full space-time topological invariance. And then, indeed, there's no chance that you can continue to be topologically invariant here, because you can deform your Gaussian surface well all the way off of your Wilson line. It couldn't be some topological invariant that's computed by this Gaussian surface anymore. And indeed, Gauss's law really breaks when you go to energies above the electron mass. The way you would think about this reading Peskin and Schroeder is just that when you probe some heavy charge at shorter and shorter distances, when you go much below the Compton wavelength of the electron, then you see the appearance of virtual pairs of positrons and electrons that screen that heavy charge. Right? So this is something that is familiar to you, but there really is a symmetry and a symmetry breaking that is associated with going from distances far below energies far below the electron mass to then when you can see the dynamical electron. And really, when you go above the electron mass, this electric one-form symmetry that you have in the infrared of the real world gets broken, because these Wilson lines can be cut. Now, parenthetically, let me mention, really what's happening here is pure electromagnetism has a U1 one-form magnetic electric symmetry. And we know the appearance of the electron breaks the continuous part of that. In fact, we don't know whether there might be a discrete electric one-form symmetry that remains at even higher energies, and still a discrete version of Gauss's law that holds. Adam and I just wrote a paper about this. This motivates from a very bottom-up argument, spending more time thinking about and looking for fractionally charged particles at, say, the energy frontier. I can talk more about that later, but let me move on now, and say also that, in line with your intuition for electric magnetic duality in pure electromagnetism, there are also there is a magnetic one-form symmetry in low energy electromagnetism as well, corresponding to the fact that there's nothing that cuts the 't Hooft lines, the line operators for some magnetically charged particle. And in fact, and so that is also some emergent magnetic one-form symmetry from some further UV theory where you have, say, 't Hooft Polyakov monopoles when you complete the standard model into a grand unified theory. And actually, I say this especially because magnetic one-form symmetries are really going to be the thing that's going to come up later on. Good. Is this a good place? Yeah, maybe this is a good place for me to pause for questions and take a drink. Or not. Fantastic. If everything's clear, that's the goal. Good. Let me turn a bit and just very quickly remind you of some other quantum field theory topics that you've surely already learned about. As you know, sometimes we have a scenario where at the classical level, your theory has a good global symmetry, say some U1x, but when you go to quantize the theory, especially when we have a chiral gauge theory, as we often do, that global symmetry can end up being anomalous in the quantum theory. The current conservation gets modified to have some FF tilde term on the right-hand side. In perturbation theory, you can compute this with some triangle diagram. This is an ABJ anomaly, as you know. And so we have now some violation of the current conservation. You can ask, well, okay, what physical effects actually cause that charge conservation to be violated? And in fact, it is instantons that just activate this FF tilde term, have some non-vanishing value there. I'll remind you, you think about instantons as some winding, some non-trivial winding of your gauge field around Euclidean space-time infinity, which is exactly what contributes to these FF tilde terms. And even more, okay, instantons violate these, but how do you U1x is some symmetry that acts on the matter fields in your theory. How do you actually see the violation of U1x in your low energy Lagrangian? Well, 't Hooft long ago wrote some fantastic, amazing papers that taught us that at low energies, you should think of these instantons as leading to some effective operators among the charged fermions in your theory that we call 't Hooft vertices, that indeed exactly violate the anomalous symmetries by the right amount. This is all some QFT review. But no, so I just told you that instantons are the field configurations that can turn on this current conservation. But in fact, we have long understood in some sense that there are some interesting scenarios where they don't. That is, for example, when your gauge group is U1, this gauge group does not contain enough internal richness to actually possess this topological quantum number that allows for instantons in R4. That is, you will hear it said, there are no Abelian instantons in R4. If you take some U1 gauge theory and you integrate FF tilde over any field configuration in R4, it's identically 0. And so the old lesson that people took from this is, well, okay, there's some formal anomaly here. The current conservation is somehow formally modified. But because of this fact of not having Abelian instantons, the S matrix, if you go and measure it in this theory, will continue to preserve this U1x quantum number. It's anomalous in some sense, but it's still preserved in the S matrix. So we can just learn as particle physicists that we can ignore this anomaly. That's great. There's one fewer thing for us to think about. If you have some U1 gauge group, you can just ignore the anomaly. And that's not a wrong lesson, but I think there is a better lesson for us to learn here. And in fact, I think as effective field theorists, we should have always been quite confused by that scenario. I think as effective field theorists, we should think if you compute some zero, there must be some sort of symmetry that is responsible for that fact. So this scenario where you thought the symmetry was anomalous and so should be broken, but it you continue to have all of these zeros in the S matrix, should have been very confusing for us. You should think, just on general grounds, as an effective field theorist, there must remain some sort of subtle symmetry that was actually responsible for those zeros continuing to be there. And you could have had a hint from this long-standing, interesting program to understand how monopoles interact, magnetic monopoles interact with fermions, which this confusion was first brought to light by Dirac, but in fact, people are still arguing about exactly what the right way to think of this is. But Callan and Rubikov separately explicitly showed that when you have a magnetic monopole around, in fact, by scattering fermions off of it, you can see some violation of this anomalous quantum number in the U1 gauge theory. So on this ground, you could have gotten a hint that somehow magnetic monopoles should be involved in what's going on with this notion of subtle symmetry here. And indeed, that's the case. As of a couple years ago, from Clay and Kentaro, and also from Yichu, Hotat, and Shuhang from Stony Brook, we've learned the right way to understand what this subtle symmetry is. In fact, in such a scenario where there's an anomaly but no instantons that saturate the anomaly, the symmetry, the global symmetry, is not fully broken by the anomaly, but is converted into something a bit more subtle known as a non-invertible symmetry. And what you learn is that the only good notion of symmetry, of global symmetry, that is still there must act now both on local fields, like you thought this U1 symmetry did to begin with, and also now on the Tuft lines, these world lines of magnetic monopoles in your theory. Roughly, it acts on the Tuft lines by giving them a small ionic charge, a small electric charge, in addition to their magnetic charge. There's a much nicer way of saying this really in the right framework of generalized global symmetries, which is to talk about something known as symmetry defect operators. And I'd love to give that introduction as well, but then I wouldn't actually be able to get to the particle physics at the end. Yes. Sorry.
Potential for magnetic.
Yeah, yes, the dual photon.
And
Thank you.
A is just normal.
That's right. Exactly. Thank you. Sorry, I should have said. Yeah, so it starts out as a Tuft loop. It's only coupling to the dual potential, but then it's getting some small ionic charge. Okay. Now, without giving you all the technical details, the conceptual lesson here is that now this is a symmetry which acts both on local operators and on line operators. So since it acts on local operators, it constrains the form of the Lagrangian, right? It can constrain which operators you can write down, local operators you can write down. But since it also acts on magnetic Tuft lines, line operators, then just like our earlier discussion of the appearance of the dynamical electron breaking the electric symmetry, one-form symmetry, when you go to some UV theory and you see actual dynamical magnetic monopoles, some Tooft Polyakov monopoles, for example, those can also cut this Tooft line, and you know then that this symmetry has to break, just like the electric one-form symmetry broke when we saw the dynamical electron.
Excuse me, is
Please.
it somehow, it's a question, is it somehow related to the fact that a magnetic monopole, let's say, of polypole monopole, requires an electric field in this, if you switch
Yes.
on theta pi?
It is related to that.
It is,
In fact,
that's what.
and if we'd gone through this construction in more detail, then indeed, you would be able to see that explicitly. That's exactly right.
So alpha is related to the theta parameter, and this is the Whitman effect.
Not, well, sort of. Alpha is a U1 phase here. This is generally, I'm describing here roughly a U1 non-invertible symmetry, right? So alpha is just an angle that, the U1 angle, right? Started with a U1 zero form global symmetry. But indeed, when you go and when you understand how to actually talk about these symmetries in this language of symmetry defect operators, it's certainly true that you mechanically see the appearance of alpha in this transformation rule I've written for the Tooft line by changing the theta angle across some symmetry defect operator boundary. That's a roughly a right way to think about it. Yeah. Sorry, yeah, there's technical details here that I can point you to or talk about later, but yes.
So why is it non-invertible? I mean, how do I see that?
Yeah, good. I don't have a very intuitive explanation for this. But I'll say the symmetry continues to act invertibly on local operators.
So on the side, so that's that part is invertible. On the zero.
Yes. If you only consider a configuration where you don't have any Tooft lines around, then it continues to act like a normal sort of symmetry. But it's actually when you think about the action on Tooft lines, basically this is very weird because you're turning the Tooft line into some improperly quantized object. And that action, it turns out, even though you should think of it as a symmetry, you have some symmetry defect operators, some operators that implement this transformation that are topological, and so should really be thought of as a symmetry. It turns out that these operators, when acting on Tooft lines, don't have any inverses. You end up with, if you try to undo this, you end up not only getting one, not getting exactly where you came, getting back to where you came from, but there are additional pieces as well. Yes. If there's any further insightful comments from the back or anywhere, please feel free.
I mean, the symmetry operators are not unitary in this case.
Yes.
So there's no inverse to them. But it's best to discuss afterward because I think we'll think too long. The French-Simon's theory, living in detail. That leads to some problems.
Yes, that's right. And again, yes.
Yeah, so if its operator is not invertible, then it should have a kernel, right?
That's true as well.
So what is the kernel in this case? That might help understanding.
Yes. The kernel is that it when you think about these acting on a time slice, they destroy the Tooft lines. I think I'm getting that correctly. Yes.
Normally, you act with a symmetry operator, you don't kill anything, it doesn't zero anything out.
That's right.
and the 10, and it's not really.
That's right.
I think it's probably.
Yeah. Please.
That's my second question.
Sure.
I'm wondering, in this particular example, let's say I do two transformation in a sequence. First, I do it with the exponent of I alpha. Then
Yes.
you get me this result on the right. You wrote it down.
Yes.
But then I do it the second time with mine e to the power minus e alpha.
Yeah.
Since everything commutes here, isn't it that?
Well, good. So
inverse.
you would think so. Really, it's rather more subtle. As we were alluding. Does this other one work better? We can see. So, actually, these transformations you need to think about as being implemented by some symmetry defect operators that in this case live on some three-dimensional surface, called this U symmetry. You should think of this as the generalization of either the Noether surface that you integrate the Noether current over, or the Gaussian surface. In the case of this non-invertible sort of symmetry, normally you'd think in either the Noether or the Gauss case, like we were talking about before, then you're just integrating some current over your space. However, in this more subtle case, the problem is, you started out with this, say, in the classical theory, but we're in this weird scenario where you have an anomaly, right? And so this actually, the current is no longer gauge invariant. This turns out not to be a good topological operator in general.
Could you please explain it in this part, not generally? In this particular example.
Yes, that's right. It is this particular example.
Forget about general considerations. This is the simplest example, probably, which you can give.
That's true.
It will strongly enhance understanding or the possibility of understanding if you just limit yourself to this example.
That's true. And that is what I was getting to here. Indeed, it turns out that the only good notion of a topological operator that you can write down in this case is not just an integral of a current, but it has to have some auxiliary field living on the topological operator that we write down that, let me see, that this is roughly the important bit that couples this operator to the magnetic one form, the two index current of the magnetic one form symmetry that lives in the bulk. And indeed, it's this extra sort of richness of this sort of topological defect that allows it to act both on operators that are zero-dimensional and on operators that are one-dimensional. But it results also in now it's no longer a unitary operator. You get a piece that's one, but then you also get some additional terms that integrate over two cycles in your space.
So in this case, let me take your equation.
Well,
let me call psi on the left-hand side of psi bar.
yes.
And now I forget about prehistory. I do transformation on psi bar or psi prime, let's say.
Yes.
With the opposite alpha.
Yes.
Then, knowing the definition of what you define here, that means that at least the local part,
That's true.
it will go back to psi.
That's right. So
now, what happens to the non-local part?
Yeah, indeed. So when you have some 't Hooft lines around, then there are some two cycles around the 't Hooft line. And there are some extra terms here that make this operator non-unitary when acting on 't Hooft lines. I mean, I should emphasize, I'm not writing some equations here, right? So this is meant to be heuristic, and it really only is heuristic. You can't, you know, to properly think about this, you need this technology of symmetry defect operator.
No, but you said that multiplication of psi by some phase, what it does, it adds to the 12th line with the same coefficient alpha.
That's right.
Regular line, how it's called.
That's right.
Wilson line or whatever.
Yes,
It's
yes.
your one theory after
Yeah,
all,
yeah.
all complex.
Yeah.
So if I do the transformation for the second time, let's say I start with a different phase, e to the power I beta.
Yes.
Then I apply e to the power I beta to what you had previously. It seems I just repeat. You add another e to the power I beta times the Wilson line. Isn't
Yeah.
it true?
No, unfortunately not, right? So that is the case when you have a normal sort of Gauss's law operator, or, right? That's when your operator is only given by, well, the exponential here, but of the integral of some current. And then you just pick up these simple contact terms when you try to move your operator past this symmetry defect operator. But here there is some richer structure that's required to actually still have a define a good symmetry. In this case, when there is an abelian anomaly.
Okay, then I'm sorry, I think it's an important
It
issue.
is an important point.
Then may I ask the following question? Can you please do such a favor? Can you take this formula, which is the only formula in this slide, and can you do another transformation with the phase e to the power I beta and see explicitly what do we get on the right? Not implicitly what you are trying to explain, just explicitly. What else do we get on the right?
You pick up some integrals of the current or the
No, don't write you bar you, write it in this form.
no, but sorry, this is only ever heuristic. You need to talk about u bar u, right? That's the point. That's
No, I
why.
want to make the second transformation on psi. Can you take psi once transformed and then I apply another person? Tony comes and says, I want to make the second transformation.
Can you replace alpha with alpha plus beta?
In the back.
Oh yeah, please.
So that is on the company correct. There is a coefficient. It's not the e by alpha.
Sure.
It's actually 1 over something.
Sure, true.
So can you write down on the board what he's saying?
I'm not. Well, I can pass it to him. But indeed, you can't think of please. She would like to come on.
It's in the best traditions of LTPI.
Okay, yeah, very good.
So this opera is the following. So this is you have had some changes.
Take another pen.
That's the only one that works, I think. Unless there's something else. Yeah.
So for example, for alpha equals k over 2 tau. So this is the operator. This small a lives on the operator method.
What is R?
That's K.
K.
K, I'm sorry.
K is an integer.
Here, this alpha is your rotation angle. So if your rotation angle takes this value, 2 pi over k, then your operator looks like this. Yeah. So here I should also put the alpha here.
So you are saying, this equation which is written, there is something else on the right.
Well, good. So
Yes.
So again, this is just heuristic because really you need this technology. What you really have to think about is moving these drawing some symmetry defect operator, this U that lives on some three-dimensional manifold, and moving it past either a local operator or a 12th line. And so what I'm heuristically giving here is the result of moving a symmetry defect operator past this 12th line.
I don't understand. So why don't you say that this formula is not correct, or it cannot be in principle written in full?
Indeed, I think yes, I tried to say that, but yes, this is just heuristic, absolutely. And like I was saying, I'll repeat. yeah, there's just another sort of half-hour-long introduction that I would have needed to give to.
Well, at least you should not mislead the audience. You
I-
should say that it's something abbreviated and what you
Oh, yeah,
abbreviated
good.
cannot be even
I-
written on this course.
Right. Sorry, yes, I did, perhaps I should have it written on the slide as well. I think I did say it. I'm trying to give enough heuristics here to get to the conceptual points that will allow us to get some interesting particle physics out of this. But you're right, this is not a technical slide, absolutely. And I should disclaim that. Very, very good. Okay, but yeah, maybe I'll go on to say some things about what you should think about this. So since we have some symmetry now that acts both on local operators and line operators, again, this entire symmetry must break when these 't Hooft operators can now be cut by dynamical magnetic monopoles that we see at higher energies. And so the symmetry structure must break. And so if I had some local operator that was protected only by this non-invertible symmetry, I learn now that this local operator must be generated when there are dynamical magnetic monopoles, when I go to high energies and see these dynamical magnetic monopoles. And so I think the conceptual lesson to us as effective field theorists is that we're learning some refinement of the naturalness principle. This goes past or is complementary to what we learned from Dirac and 't Hooft. We are learning that if you see in your low energy theory a spurion for a non-invertible symmetry, then that operator can be generated by some non-perturbative gauge theory effects in a UV theory that includes the correct magnetic monopoles, right? And so this is more powerful in some sense than what you can learn from technical naturalness, right? Which just tells you whatever hierarchy problem or tuning problem you're trying to solve could be solved at high energies and then is radiatively stable as you evolve to low energies. But finding that a parameter is technically natural doesn't give you any insight as to what sort of mechanism might have actually produced that small value to begin with. Whereas, because of this interplay between one-form symmetries and zero-form symmetries, here we are learning about an interesting non-perturbative way that certain coefficients can be generated in some UV theory that completes our infrared theory. So I think this is more sort of powerful. And in my two examples, I will use this sort of reasoning to find some Dirac natural models. In the lepton sector, this will be a nice Dirac natural model for a Dirac neutrino Yukawa, which is already technically natural, but we'll write actually a Dirac natural model. In the quark sector, this will be a Dirac natural model for theta bar, which is not even technically natural in the low energy theory. Please.
So up to here, you are explaining about like a U1 chiral anomaly, right? So is there any other anomalous symmetry?
There is. We will get that. We will get there. Very good. Indeed. Okay. Okay. So concretely, model building strategy. If you find in your low energy theory that you have a symmetry that protects some operator and has an anomaly, that symmetry has an anomaly, but some of the values of the instanton number are not realized on R4, then you learn that there's a non-invertible symmetry and that this operator could be generated by some non-perturbative gauge theory effects. We all know the standard model. We should say often and loudly that it is absolutely amazing that we understand the theory of nature of us down to distances of 10 to the minus 19 meters. This is a fantastic achievement of humankind. But we cannot rest on our laurels. We know it's incomplete. And one simple way to go beyond the standard model is to gauge some of its approximate symmetries. This is actually very familiar, right? Whenever you do some grand unified theory, SU5 works so nicely because the standard model has an approximate SU5 global symmetry that you're upgrading to a gauge symmetry when you do the unified theory. Yes?
Back to this other point. I mean, if I take, for instance, the massless up quark solution, right?
Yes.
We know that we can guess the size of the breaking due to instantons, it's e to the minus action. Right?
Yes.
So isn't that equivalent to what's happening here? So, I mean, what's happening on the previous transterm? Or the
Yeah.
Here, right? You were saying that.
I'm saying that there is a systematic.
This is powerful, but we kind of already knew that for instance.
This is a systematic way to search in an infrared theory for when there are some minimal UV models that contain some new instanton effects. And it's not the only way to get some small instanton effects, as you know, but this is.
But let me say it another way: can instantons always mimic what you're going to say with these generalized symmetries?
Well, it's not mimic. They're going to realize what I'm going to say.
Yeah, okay,
right?
they're going to realize it.
Yes, as far as I think the answer to that truly is not entirely clear. As far as I'm aware, in all the examples written down, indeed, from the UV perspective, this ends up being an instanton effect that in principle you could have written down 40 years ago, but no one had in these examples. Deeply, I think the answer is not entirely clear if that's the only thing that will end up happening in the UV theory. Yeah. Well, yeah, maybe in fact we know it's not, but it's difficult. Anyway, yes.
I have a model, right? I have a parameter that is technically natural, right? So the way you're going to apply your analysis is I hope to find this technically natural parameter correspond to some spurion non-invertible.
Yes.
Or the working assumption is this will be a small parameter, right? It seems like all the ways you're writing here is assuming it's a small parameter and it's like exponentially suppressed. So what gives this form? Right? In principle, a spurion for a non-invertible symmetry can be of any size. Right?
Yeah.
That's the base at where I start to do my perturbation around that symmetry. So it seems like all what you have realized, it has to be small and instant like generate.
Well, I'd say when you have a small coefficient, that's the place where we need some interesting UV theory that has some non-trivial dynamics and creates the small value. If you find a spurion and it's order 1, then you don't need to do anything fancy. You can just assume some random theory and you'll end up with that order 1 number, right?
So where does smallness come from? Smallness come from you want to make it a reasonable perturbation of the original symmetric theory. Or all the known ways to generate the size of such spurion is instantaneous surprise. Oh, let me answer differently, right? So I can have order 1 parameter. I can also have a very big, terrible parameter.
Sure.
Right?
Yeah.
So why don't I use your answer?
But there's nothing you need to explain in that case, right? I'd say just some random UV theory should be able to achieve an order 1 symmetry breaking parameter, right?
Yeah, order 1 big parameter.
Oh,
maybe
well.
this theory become non-perturbative.
Then I have no special insight into it.
Inside, you have new theory.
Good. But I mean, that would tell me that the symmetry is I guess very badly broken in a way that you don't have any control over. Seemingly, I mean, it's an interesting thought. Maybe we can return to it after I go through these examples.
Yeah. So the game now is I find small parameters in the standard model and try to give them a UV story.
Yes, and try to see if there's a nice theory where they are a spurion, not just for a normal sort of symmetry, but for a non-invertible symmetry. And then you can be led by that to a nice UV theory. That's right.
All your examples, it's all going to be instanton physics at the end of the day.
That's right. From the UV perspective, it will all be instanton physics in these 2 examples. Great. Very good. I did that slide already. Yes, standard model. We're going to go beyond. I'm going to talk about the horizontal symmetries. When you turn on the Yukawas, you guys know this, so I'll not say much of anything. When you turn on the Yukawas, in the quark sector, we break to baryon number. In the standard model with massless neutrinos, then we have these 3 separate lepton numbers. And as you know, you have to take into account the SU2 anomaly, and you get the B minus L as anomaly free, and also these lepton flavor differences. Very natural, starting from the standard model, to think about gauging some of these symmetries. And indeed, we're going to go beyond by gauging L mu minus L tau. As you probably know, this is very phenomenologically well motivated. People think about this for the structure of the neutrino mass matrices, for B anomalies, for G minus 2 of the muon, lots of good reasons to think about L mu minus L tau. And now when I gauge L mu minus L tau, there is another sort of ABJ anomaly to consider. And in fact, indeed, in this gauge theory, the other lepton family difference symmetry, which is just a global symmetry here, does become anomalous. There's a coefficient, anomaly coefficient of -1. And so far, I've just taken the standard model and gauged L mu minus L tau. On the next slide, I'll add some right-hand neutrinos. But so far, this is something I can do without adding anything. And indeed, we're in exactly this scenario where you have now some current, formally, some current non-conservation for, say, the LE minus L mu global quantum number, and this FF tilde for this abelian gauge theory on the right-hand side. So we're in exactly this scenario where you have a non-invertible symmetry, this LE minus L mu non-invertible symmetry. And let me point out, yes?
If you just add one instanton to the standard model.
Add one instanton to the standard model. I don't know what that means.
So consider one instanton or add to the Lagrangian effective contribution of one instanton.
Okay.
Then you see that simultaneously with this you mean separate muon conservation and electron, right?
Yeah, so I'm going to
What
gauge.
is written? L, what is non-conserved? L minus E minus mu, right?
Yes, yeah, the other lepton family difference is now formally anomalous, but it's one of these abelian anomalies.
Mu minus tau.
Yeah, so again, mu minus tau is a gauge symmetry at this stage. LE minus L mu is still a global
But
symmetry.
doesn't instanton contribute to the right-hand side? Instanton, if you
Which instanton? So LE minus L mu is in the standard model anomaly free. So there are no standard model instantons that
so
break
what
LE
is the
minus.
contribution which breaks it, this which make it anomalous?
So it's L mu minus L tau. Now that I've gauged L mu minus L tau, there's this new anomaly diagram.
So he's gonna add magnetic monopole that you want, right? That's
Yes,
what he's gonna do,
yes.
right?
That's right. Yeah. So currently, it's in this stage that we've been talking about, where you have the anomaly, but there are no instantons. So in this theory, the S matrix would continue to preserve LE minus L mu. Yes. So we have a non-invertible symmetry here.
And mu minus tau, you say they are conserved,
I've gauged L mu minus L tau. Yeah. So it better be conserved.
okay. So you say that in the standard model, beyond the excitation separately, neither, it's only the total leptonic charge which is conserved, right?
That's right.
So muon can pass into on the, I don't know on what configuration it can pass into electron, right?
No. No. Sorry.
Into tau. Something should follow from this equation in physical terms. What is non-conserved in terms of the physical process?
Sorry. Now we're talking about the standard model.
Standard model.
In the standard model, what's non-conserved is that SU2 instantons or sphalerons in the early universe can turn 3 baryons into 3 leptons, or the other way around.
B minus L non-conserved.
B plus L.
B plus, okay.
That's right.
Okay.
That's what happens in the standard model.
B plus L.
That's right. But that's the only anomalous process.
Okay, and to which model is your previous slide?
Now I'm going to take the standard model and I'm going to gauge L mu minus L tau. So I'm going to gauge one of those anomaly-free global symmetries.
Okay. M minus, you gauge M minus tau, mu minus tau.
That's right.
So there are no such gauge boson in the standard model.
Certainly not in the standard model. So I'm going to,
And if you add to the model, don't you ruin the model completely if they are dynamical gauge bosons? Don't you ruin this model?
so of course it has to be Higgs. That's true. This is, now I'm considering some UV completion or UV theory to which will flow to the standard model at low energies.
Okay.
That's right.
Okay.
And typically, things that give masses and mixings in the mu and tau sector has to occur at the lower energies.
Yes. Yes. When you do that Higgsing, then you can populate the off-diagonal parts of the matrices. That's
So
right.
you say this is just a mixing mass term which mixes mu and tau?
Right, if you just insist on a symmetry and you write something like a neutrino mass or neutrino mixing, it often doesn't agree with this.
Of course, if you mix, I mean, if you
Yeah.
didn't diagonalize the mass matrix, that's for sure.
Yes.
Okay.
But in the UV, this is allowed. That's right. So I've gone to some further UV theory, and we found that there's a non-invertible symmetry here. In fact, the important part of this non-invertible symmetry is a Z3 subgroup, which is generation independent. That's just if you take this global symmetry, LE minus L mu, that we determined is non-invertible, and you add a gauge charge, then because -2 is equal to 1 mod 3, then that's just lepton number. And so there's a Z3 subgroup of lepton number, which is non-invertible in this L mu minus L tau theory, and that disallows neutrino masses or protects neutrino masses.
And why is this lepton number? Because if you LE minus 2L mu plus L tau,
If you only take a Z3 subgroup, then that's just lepton.
it's not the lepton. Lepton is the sum of all E, mu, and tau.
That's right. But if I take a Z3, if I only look at a Z3 subgroup of the transformations, not the full U1, then -2 is equal to 1, or -1 is equal to 2. Either way. That's right. This is just a nice way to see that actually this symmetry disallows all of the neutrino masses. And so we could follow this general model building guideline by finding this non-invertible symmetry. We could go and write down some UV theory that includes those magnetic monopoles and will generate an exponentially small Majorana mass. Now,
so what you are saying is that if you imply that there is this symmetry,
yes.
which you had, then this will rule out all this mixing between, let's say, between in the lepton masses.
Yeah, at high energies, right? And so then that mixing has to come as you flow downward to the standard model.
Yeah.
It comes from the Higgsing of that theory. That's right.
I
I mean, this is just the same story as the horizontal gauge theories that people have been exploring for decades.
see.
That's right.
Thank you.
Yes. Good. Actually, I think more exciting than the Majorana case is if I go and add now the right-handed neutrinos and replay this story, then again, in fact, there is a non-invertible symmetry. You just need to do a little bit more algebra to write down exactly what it is. But the important part is now a Z3 subgroup, which charges the standard model leptons like lepton number, but gives right-handed neutrinos the reversed sign. And now this non-invertible global symmetry disallows both Majorana and Dirac mass terms. And so now I think this is more exciting model building logic to follow then, because of course, if neutrinos are Majorana, then as we know, there's some good reason for them to be different and special and have, we know the seesaw mechanism very well. But if neutrinos are Dirac, then it seems very puzzling as to why their Yukawas would be so much smaller. Their masses would be so much smaller, right? For Dirac neutrino Yukawas, the largest neutrino Yukawa is something like 10 to the 11 smaller than the tau Yukawa, the largest charged lepton Yukawa. But having found this non-invertible symmetry, now I can look for a UV theory that includes L mu minus L tau magnetic monopoles, and I will find that non-perturbative gauge theory effects in that theory generate this Dirac neutrino term. And so once you have that guidance, you know where you should be looking. It's not so hard to find the nice, beautiful model to write down. You still have to be a good quantum field theorist and particle physicist and model builder. But in fact, the very nice thing to do is to upgrade this U1 L mu minus L tau gauge symmetry to a full non-Abelian SU3 lepton flavored symmetry. And so the three different flavors of each lepton are just unified into a triplet or an anti-triplet under this gauge symmetry. And then what you can do in this theory, like we learned we should be able to do from the infrared, what you can do is you can write down only the charged lepton Yukawa classically. This is a flavor gauge symmetry, so of course it's flavor symmetric. And then when you run to lower energies, there are instantons of the SU3 gauge theory that have some Tuft vertices that look just like this. It's very simple in this case. The right-handed leptons get 1 0 mode each. The left-handed, because of SU2L, get 2. And if you take this Tuft vertex and close off the charged lepton line with an insertion of the charged lepton Yukawa, then these Tuft vertices generate for you a Dirac neutrino Yukawa that comes from the charged lepton Yukawa, but is suppressed by an exponential of the instanton action. And so automatically in this theory, you get exponentially suppressed Dirac neutrino Yukawas. Please.
But you said that all this works if you can produce monopoles, right?
That's
real in the real world. But unless you in the standard model per se, there are no, you have to embed it in SU5.
Good. So these are not electromagnetic magnetic monopoles. These are magnetic monopoles of L mu minus L tau. And so
you add additional gauge bosons.
Exactly.
Okay.
So now I'm starting with a full
Okay,
non-Abelian horizontal symmetry.
So it's extended standard model.
Oh, yeah, absolutely, yes. Well, I'm a BSN physicist. That's right. Good. Okay. So I at least I won't because we've done it, but I think this is I was pretty amazed to find this. I would have told you a couple years ago probably neutrinos are Majorana. Certainly people had written down Dirac neutrino mass models. Usually those require a fair amount of extra structure. So I was pretty amazed to find that essentially the standard model fermions have it within their power already. Of course, we have to have right-hand neutrinos, but this is just a gauge theory of the standard model fermions, and they have it within their power already to give you exponentially small Dirac neutrino Yukawas. 4-dimensional weakly coupled gauge theory. Please.
What is the White House star? Is that UV parameters in my theory, or is it?
Yeah, sorry. So this is a flavor gauge theory. So this is a flavor symmetric charged lepton Yukawa. Yes.
And so this SU3 sub H is get fixed somehow?
Yes, absolutely. So I mean, very true.
But the instantons are still large.
Well, they don't have to be large because I want to get a number that's 10 to the minus 11. But indeed, what I've really done here is just exhibited an overall very tiny Dirac neutrino mass scale. You're very right. I haven't said anything about the texture yet. That does need to come from when you Higgs SU3 eventually down to nothing. Like you get back to the standard model. And in fact, Gonzalo Alonso Alvarez and Jim Klein wrote a nice paper on how you can do this Higgsing and get something realistic a few years ago. Very good. Okay, I'd like to, Evgeny in his email inviting me, asked me actually to talk about the quark paper. So I'd like to get there. If anyone needs to leave, I won't be offended, of course. But indeed, once we'd written down this lepton model, I was convinced for a long time that there had to be something interesting to discover in the quark sector. Because really, there's a structural parallelism in the standard model between the leptons and the quarks. The quarks are just the leptons with color, but it's a more subtle story. It took us a while to understand exactly what it was. And you might say, you know, what do we, I don't need exponentially small quark U powers. That's certainly true. In the quark sector, there's this even more severe naturalness issue, which is the strong CP problem. Right? Just very briefly, in the strong sector, we have this CP odd parameter, which is the imaginary part of combining the determinant of the up and down quark U powers and the SU3 theta angle. And we know from neutron EDM experiments that the imaginary part compared to the real part of this is less than 10 to the minus 10. Normally you talk about this in theta bar. I like the Cartesian coordinate picture because, well, it confuses people with the massless quark solution, like we'll see in a moment. Anyway, but okay, so on general grounds, this is very surprising, but in fact, as you know, it's even worse because in the standard model with more than 2 generations, there is more CP violation in the theory of quarks. And with 3 generations, there's 1 more CP violating angle, the CKM angle. And here we've measured the CKM angle to be order 1. So there's this humongous hierarchy between the 2 different sources of quark CP violation, which is very puzzling. And it means that theta bar, or the strong CP violation, is not technically natural. Very puzzling. Please.
More or less died already.
Because
there are so many things which cannot be, I mean, so many elements of naturalness which are seen already to be not valid in experiment.
I would
So
not.
you maybe take one element with the theta, but there are many parameters which are not natural, which we see at LHC.
I'd say there it's mostly the one, which is the Higgs mass. Oh well, we don't see that at the LHC. But you're right, of course. Indeed, certainly the naive way people have been thinking about naturalness is not fully correct. I think it's hard to get really away from naturalness in a quantum field theory, in our current understanding of quantum field theory and Wilsonian renormalization. As to the hierarchy problem, yeah, something somehow more subtle is going on.
Higgs mass.
Yeah, the electric hierarchy problem.
So what else do you need to forget about naturalness? I'm not even speaking about the vacuum energy density, right?
What else do I need to forget about naturalness? I would like to have. I would like.
Higgs mass is extremely unnatural.
Well, it's unnatural by a factor of 10. We know that, and indeed, that's a big problem. And you know, I spent. I think about the hierarchy problem a lot, and that was the subject of my thesis. And a lot of my
we're talking about non-supersymmetric model.
Yes.
In non-supersymmetric model, there is quadratic correction in the mass of the T quark.
Yes.
It's pretty large.
Yes.
So it shifts far away from this to 1 to 6 or 1 to 7.
So we know. Well, we know in some. What should I say?
Okay,
I
agree with you that order of 10 is the upper bound.
Yeah.
How much? It may be 100 or we don't know.
You know, there could be. I'm all in favor of some radical ideas about.
It's enough to kill nature.
That I disagree with. That certainly I disagree with. Right? For all I mean, in some
Okay,
very.
Tell us how do you save naturalness in the standard model?
Well, we have to go beyond the standard model, of course. As you know, people have proposed all sorts of modules that could be responsible for explaining a little hierarchy between the Higgs mass and some supersymmetric particles.
But have you seen these models? They are monsters. They're much worse than anything you can. On one hand, you can say, forget about naturals. On the other hand, you have to accept all these monstrous models, which are artificial. They have lots of ad hoc things.
I think a copy of the standard model is is not an awful price to pay.
It's a matter of taste.
I sympathize with what you're saying, but I think maybe, demanding that, in one talk, all naturalist problems should be solved, would be a little bit too strong.
That's true.
So you just want to solve one problem and leave the rest.
Quark's idea definitely was to solve all naturalist problems.
That's true.
So that-
Now
Well-
they are more or less solved by the anthropic principle. That's the
Well,
only solution
I don't-
to the naturalist
But this
problem.
I don't know about that.
anthropic, but This one's not
Yeah.
anthropic.
This is not anthropic.
Yes.
That's why people still want to solve this.
Yes. Very good. Some good cultural commentary. So I would like to still try to solve the strong CP problem. Let me remind you, there was this beautiful idea of how the strong CP problem could have been solved even in the standard model itself, known as the massless up-quark solution. To remind you of the structure, if you think about just having one generation of quarks, the idea is in the UV, you impose some Pechi-Quinn symmetry, say that just rotates the right-handed up quark. Pechi-Quinn meaning it's some anomalous symmetry. But if you impose the symmetry, then the Lagrangian that you can write down at the UV scale does not have a Yukawa for the up quark. You just have this down quark Yukawa and the theta term. And since it's a Pechi-Quinn symmetry, well, already from the definition of strong CP parameter, it's 0 here, but you can make that even more explicit by doing an anomalous rotation, a field redefinition of the right-handed massless up quark, and that sets to 0 this theta angle, and manifestly you only have the down quark Yukawa, everything's real. Manifestly there's CP conservation. Now, of course, when
So I'm going to say that in nature, up quark is massless.
well, very good. So that is a feature of the solution, as I think you know.
It
Sorry.
already lasts for, I don't know, 40 years. So from time to time, people continue to say.
No. That's
that
exactly
the
no. I agree.
up
No.
quark is massless. It cannot be massless
That's
due to
right.
low energy day.
That's correct. We're agreeing. We know now, after some heroic efforts by lattice physicists, that this doesn't work. The QCD instantons generate some mass for the up quark, but it's not, the QCD instantons are not powerful enough to generate all of the observed mass. Very correct. And so what we'd like to ask, now that we have some symmetry-based tool to diagnose from a low energy theory when there can be interesting UV instanton effects, what I'd like to ask is, can there be some minimal UV model where new instantons, small instantons, can revive a sort of massless up quark solution?
But let's forget about it. We know from low energy phenomenology, from chiral theory in combination with all we know from pions, kaons.
So
and
it fails in the
we-
standard model.
We know that up quark has a mass.
I agree.
And it's not very small.
It's pretty small. Well, I agree. It doesn't work in the standard model. I'm going to go beyond the standard model.
Okay,
Right,
so you invent something in addition. You are not going to say that the quark mass is mass, the quark.
I will say that in the UV, it will be massless, just like in the original massless up
These
quark.
are the new contributions which will generate it large enough.
Okay, so what's the
The
point?
point-
When you read it is massless, but now.
No, but that will continue to solve.
An axiom. Point is, it's not gonna have an axiom.
But it's gonna be some sort of then
No way.
discrete symmetry or
How
something
can
where
you-
you impose the.
That's so.
No, it'll be a Pechi-Quinn symmetry in the UV.
So you'll have this use, you want pitch.
But if it quark is massless at the UV, we wouldn't see what we see at.
No, that's not right. There can be.
Physics. Read below energy data.
That's right. Yes. If you expected me to give you new physics within the standard model, that's a very high bar. We're going beyond the standard model certainly, and we're going to do something similar to what we did in the lepton sector. There's a lot of discussion of L mu minus L tau and these sort of lepton family differences, but you can think likewise about gauging some quark family differences. because there's this parallelism between the two. These are broken more because the quark Yukawas are larger, but that's fine. In the UV, they can still be good symmetries. And in fact, there's something more subtle that you can do in the quark sector because of this special mysterious fact that we have the same number of colors of QCD and generations of standard model fermions. In the following way, one combination, which is anomaly-free of quark family number that you can gauge, is something like B1 plus B2 minus 2B3, or some cycle. And because you have 3 colors and 3 generations, you can gauge this in a way that has non-trivial global structure with SU3C. Now, there's some other introduction I would give to about global structure. Roughly, you should think that this factor modding out by this C3 means that you're identifying some large gauge transformations in the one group with the other group. So if you go far away from the origin in this flavor gauge symmetry, you end up back in the color gauge group. Okay, and gauging the flavor symmetry in this way, you can also think about doing that upgrade from U1 to SU3 that we did in the lepton sector. And again, there's some non-trivial global structure that you can have. You could have seen that just by writing down that flavor gauge theory chart quantum number assignment and noticing that the quarks already have this exact quantum number. And when you have either one of these, when you have this non-trivial global structure, the topological data of your theory changes in a crucial way. And this is, oh yes, please.
So you're going to use some instanton like effect to generate from a massive up quark in UV to the massive up quark.
The down quarks, in fact, but yes.
Right now, it does not generate another strong CP power, another theta angle.
Which other theta angle?
UVI rotate and absorb.
Oh, well, good. I'll tell you what, I'm going to tell you what the solution is. What yeah, you think I'm going to leave you hanging? Come on. Indeed. Good. So there's a non-invertible symmetry here as well. You have to do the analysis. It's slightly more technical now because it's not just a U1 chiral anomaly. There's some anomaly that the SU3 theory always has some instantons, some integer valued instantons. But when you have this non-trivial global structure, in general, the instanton number can actually be fractional. So now this will be a story about some fractional instantons that don't exist on R4, but only on some more general spacetimes. You have to do some more subtle analysis that I won't go into. You have to see which you have to look at all the global symmetries you have and check which are broken, which have anomalies with integer instantons, in which case they're just broken, and which only have anomalies with fractional instantons, in which case, again, you have a non-invertible symmetry. And in fact, the non-invertible symmetry here is, again, some Z3 symmetry that looks structurally identical to what we saw in the lepton sector. You have Q and U with the normal baryon number of charges, and you give the wrong sign charge to D. And in either of these quark flavor gauge theories with this non-trivial global structure, now this becomes a non-invertible symmetry, and the down quark Yukawas become a spurion for this non-invertible symmetry. So again, we can follow our model building logic. We have a classical global symmetry that protects the down quark Yukawas, and it has an anomaly, but not all of the instanton numbers are actually achievable on R4. So again, there's a non-invertible symmetry, and we can think about going to a UV theory that introduces the correct color flavor monopoles that will violate this non-invertible symmetry. And indeed, again, you still need to be a good quantum field theorist and particle physicist and model builder, but from this guidance, you can find what we